Welcome back. So we've done a lot of discussion on the unit circle and this angle in standard position with its terminal side intersecting unit circle at point P, and we've used the x and y coordinates of that intersection to define sine of the angle t to be the y coordinate of that intersection, cosine of the angle t to be the x coordinate of the intersection, and then a whole lot of other things, right? But I want to focus on these two for now. So thus far, it's been pretty theoretical in the sense that I could come up and give you an angle and say, well, here, let's imagine there's an angle theta that intersects the unit circle at a point -5/13, 12/13. And I just gave you that. Then you could happily claim, using this angle theta, that the sine of angle theta is the y coordinate of that intersection, and cosine of the angle theta is the x coordinate of that intersection. But we didn't really discuss how we could really find that angle or do much with it. But then we got a little bit more tangible by saying, oh, there are these special triangles. Specifically, let's imagine the 30, 60, 90 triangle. So if I sketch this like this, the 60-degree angle right here, we said that was pi/3 radians. And if we make the hypotenuse 1, then what happens is this side becomes √3/2, and this side becomes 1/2. And we did a proof of this 2 lectures ago. So if we take this and we place it in the circle, in standard position, we can say that this point right here with an angle pi/3 in standard position is this triangle just inside the circle. So we could say, oh, the x and y coordinates of this intersection must be 1/2, √3/2. And then we were able to use that information to say that sine of the angle pi/3, which is an angle we understand, this has a definite value of √3/2. And then that cosine of pi/3 has the value 1/2 corresponding to the x coordinate here. So today, our goal is going to be to use right triangles to get a more tangible sense for sine and cosine functions. So here we have the unit circle, and I have an angle here. I'm going to go ahead and call it t. I don't really know the measure of this angle. And it turns out the intersection point has coordinates 4/5, 3/5. Now, in order to understand this idea better, I want to consider the triangle that's formed by dropping a straight line from the point of intersection down to the x-axis. And I want to consider this triangle, which has side lengths 4/5 and 3/5. If I were to draw a bigger version of this, where I said the hypotenuse is 5, the base side is 4, and the height is 3, then perhaps you can be convinced that this triangle and this triangle are similar triangles, meaning that their sides occur in the same ratio of 5:1. And based on what we know about similar triangles, that means this angle right here has to be the same angle as that. This is t in radians. So then if we think about the relationship between any triangle and the version inside the unit circle, we understand that we would need to take a triangle and shrink it down by a factor of the hypotenuse, so the hypotenuse would become 1 and fit in the unit circle. So we understand then that sine of t, which is going to be the height in the unit circle, is going to be the opposite side divided by the hypotenuse. So we say sine of t is equal to the opposite side divided by the hypotenuse. And then for cosine, we would need to take the base and divide by the hypotenuse. We call this the adjacent side divided by the hypotenuse. Adjacent because it's right next to the angle in question. And then finally, to get tangent of t, we would take sine of t divided by cosine of t. The denominators would cancel, and we'd simply get opposite over adjacent. And this structure we often teach in geometry as SOHCAHTOA. And we mean sine of an angle is opposite over hypotenuse, cosine of an angle is adjacent over hypotenuse, and tangent of an angle is opposite over adjacent. Perhaps this is familiar to you. So to generalize this idea, let's consider a right triangle with vertices labeled capital A, B, and C. Opposite of the vertices, we'll label the sides lowercase a, b, and c. And angle A, why don't we label this a cool letter like theta? So then, if we look at sine of angle theta, then opposite over hypotenuse would be a over c. Cosine of theta is adjacent over hypotenuse, b over c. Tangent of theta is opposite over adjacent, a over b. Then we can keep going. Cosecant of theta is the reciprocal of sine of theta, so this will become hypotenuse over opposite. Secant of theta is the reciprocal of cosine of theta, so that's hypotenuse over adjacent. And then cotangent of theta is the reciprocal of tangent of theta, so that becomes adjacent over opposite. Great. Now, there's something amazing we can notice if we look at this angle B right here. And we say, the interior angles of a triangle have to add up to 180 degrees. There's already 90 degrees here, which means these two angles must add up to 90 degrees, also known as pi over 2 radians. So this angle right in here is pi over 2 minus theta in terms of angle measure. And so if we look from angle B's perspective, and we say cosine of angle B, which is pi over 2 minus theta. From this angle's perspective, adjacent over hypotenuse is a over c. Notice that it matches this, because from theta's perspective, opposite is the same thing as adjacent from the complementary angle's perspective. And in fact, we can state, at least for right triangles, that in general, sine of angle theta is the same thing as cosine of the complementary angle. And it works the other way around too. If I take the sine of pi over 2 minus theta, then that would be, from this angle's perspective, opposite over hypotenuse. That's the same as cosine of angle theta. So we will say cosine of angle theta is the same thing as sine of the complementary angle. And then we say, oh, sine and cosine obey this set of properties. We're going to call them cofunctions. Perhaps apt, because we have sine and cosine. So then if we look at tangent and cotangent, so let's take a look at cotangent of pi over 2 minus theta. That will be, from this angle's perspective, adjacent over opposite, because it's the reciprocal of tangent. So this will be a over b. Oh, in fact, that does match tangent of theta. And what if we take tangent of pi over 2 minus theta? This is going to be, from this angle's perspective, opposite over adjacent, which matches the cotangent of the original angle. So we can write it like this. We can say tangent of angle theta is the cotangent of the complementary angle. We can say cotangent of theta is tangent of the complementary angle. And then, because of this pair of properties, we say that tangent and cotangent are cofunctions. Tangent and cotangent. So the final pair, we'll look at cosecant and secant. So if we say secant of the pi over 2 minus theta angle, this is going to be the reciprocal of cosine of that angle. That will be c over a, hypotenuse over adjacent. Then we'll look at cosecant of pi over 2 minus theta. That's the reciprocal of sine of pi over 2 minus theta. So this is going to be hypotenuse over opposite. And we look across and we notice they are once again matching. So the final pair we write down is secant of the angle theta is cosecant of the complementary angle, and that cosecant of an angle is secant of the complementary angle. And finally, we say secant and cosecant are cofunctions. Cool things. Now let's come back to this picture. So in the unit circle, we have this triangle. And this triangle is similar to this triangle, which means the angle measure t is the same in each case. So if we had the ability to take a protractor and measure this angle, or perhaps measure this angle, we could immediately know what angle t is. Well, let's use a protractor. So in the calculator setup, I have the same unit circle and the same triangle. I'm going to use geometry, measurement, directed angle, and I'm going to find that this angle is 0.6435 radians. So I know this. And if I turn this into degrees, I can just click the button and it'll convert for me. 36.87 degrees. I'll place this back in here so we understand where it came from. Okay, so the logic then is I can take a triangle that's enlarged or shrunken as long as the ratios of these sides stay consistent, then my angle will necessarily be 36.87 degrees or 0.6435 radians. That's how similar triangles work. Which then means if I start measuring, so I can make a table and say I'll have all of these angles t. I can do 1 degree, 2 degrees, 3 degrees, 4 degrees, or perhaps I can do this in radians. It doesn't particularly matter. And I map out the sine of that angle and the cosine of that angle using either the opposite over hypotenuse, adjacent over hypotenuse technique, or inside the unit circle, the y-coordinate for sine and the x-coordinate for cosine. I can make a table like this, and that is going to help me understand all the values of sine and cosine. We've done this before in problem sets. So here, I have done such a thing, where I have a column with the angles, and I have the values of sine, which are going to be the y-coordinates, and the values of cosine, which are going to be the x-coordinates. And I've abused the calculator's ability to measure things very quickly. So we notice that the y-coordinate increases as our angle increases counterclockwise because we're climbing up along the y, and our x-coordinates, the cosine, are going to decrease from something very close to 1, and they get smaller as we move counterclockwise because the x-coordinate is decreasing. So these are trends we notice. And most importantly, ancient mathematicians did this, and they made tables, and they had a very good understanding of trigonometry and sine and cosine. So at this stage, we now have equivalent definitions, at least in the context of right triangles, where we have a function that uses an angle as an input and produces these as an output. Now, this is not ambiguous because these are actually the same thing. So I can write either this or that, and I will have the same value. And I have a table now that has input values and output values. So doesn't that mean I can think about an inverse where I say sine inverse of the y-coordinate on the unit circle will give me the angle. Now, this is the same thing as saying, go make that y-coordinate on the unit circle and use a protractor to measure the angle. But we don't have to use a protractor every time if we have the table. Similarly, we can say sine inverse of the opposite over hypotenuse will tell us the angle. This is the same thing as taking a protractor and measuring the angle, but now we have a table. We don't need a protractor anymore. The work has been done for us. Now, let me try to convince you how cool this actually is. Let's imagine I have a triangle, and I know this has an angle of 20 degrees, which is the same thing as pi over 9 radians. I happen to know the hypotenuse is 12 units long, but I don't know what either of the leg lengths are. I'm going to label them variables. Now, I understand that sine of pi over 9, which is the same thing as sine of 20 degrees, because these angles are equivalent to each other, is the opposite over the hypotenuse in this right triangle, a over 12. So if I have a way to know what sine of 20 degrees is, then I can take 12 and multiply to the other side and say 12 times sine 20 degrees. But see, in this table, I have a value for sine of 20 degrees, which means this number is known. I can write this as 12 times I'm going to round to 4 decimal places here, so 3420. And I can calculate this. I will go ahead and make a new calculator tab and punch in 12 times 0.3420. 4.104 rounded to 3 decimal places is the length of this height in the triangle right here. And so in fact, because my calculator has this table stored internally, I can write 12 times sine of 20 degrees. And I'm going to hit the pi button in the lower left corner of the calculator panel and put the degree symbol there. If I do this, I will get the same value. Now notice I'm in radian mode. So if I'm in radian mode and I want to punch in degrees, I actually have to put the degree symbol. Let me show you what this actually looks like. If I type in sine of 20 degrees, I get this value, which is what I'm expecting. If I type in sine of pi over 9, I should get the same value. Also what I'm expecting, because pi over 9 radians is the same thing as 20 degrees. However, if I get sloppy and I type in sine of 20 and I hit enter on this, it's a completely different value. Why? Because this 20 is being interpreted as 20 radians, and 20 radians is not the same thing as 20 degrees. So if you don't want to put the degree symbol, sometimes I like to get lazy, I need to change my mode to degrees. That means it's interpreting every number by default as a degree. So if I type in sine of 20 now, it will understand it as sine of 20 degrees, and it will give me the value I'm expecting. So you just need to make sure you're cognizant of which mode you're in, and if you're ever worried, make sure you type in the degree symbol, or if you want to use radians, you can type in, I will do this as pi over 9. I'm going to copy paste this, and I will place a radian symbol using control book and then the little r superscript right here. If I do that, then I will get the proper value. Okay, just be careful. Now, let's return to this. We can also find the other missing side. So if I say cosine of 20 degrees is adjacent over hypotenuse, I can write cosine of 20 degrees is equal b over 12. And since cosine of 20 degrees is a number that our calculator knows, it's stored internally, I can multiply 12 to the other side and say b equals 12 times cosine of 20 degrees. And I can calculate this very simply by saying 12 times cosine of 20, checking my mode. I'm currently in degree mode, so I don't have to put a degree symbol. I'll just hit this, and I get 11.276. That is going to be the length of this base. So all we need is one of the acute angles and one side, and we can completely solve the triangle. Now let's take a look at another triangle. Let's say this time we know 2 of the side lengths, but we don't know any of the angles except for the 90-degree angle. But what if we label this angle theta? We can write the tangent of angle theta is opposite over adjacent. And the calculator has a table with values of the function tangent in it, which means we could probably do an inverse and say use the output now as the input for the inverse. This should give us as an answer the input for tangent. So if we take this and hit the trig button on the calculator under control, there's a tangent inverse button. If I go 5 over 6, then before I hit enter, I should check my mode. I'm currently in degree mode, which means when I enter this, I will get a value in degrees. So this is saying the angle theta is 39.806 degrees. If I change my calculator mode to radians and go back and enter the same thing, I will get an answer in radians because my mode is radians. Once again, we have to be very careful. 0.695 radians. And of course, just to confirm that there's justice in the universe, let's take this value in radians and convert it using 180 degrees for every pi radians. I can hit the pi button, or I can type pi. If I hit this, I do indeed get 39.806 degrees. Okay, there is justice in the universe. So now we do have this angle measure, 39.806 degrees. We know that these two angles are complementary, so we could say this is now 90 minus this, it's 50.194 degrees. And then we can find the hypotenuse by using the Pythagorean theorem, right? The Pythagorean theorem always works for right triangles. So if we call this c, we can say c squared equals 5 squared plus 6 squared, which means this is 25 plus 36, so c squared is 61. And then we take the positive root. Unfortunately, this cannot be simplified, so we simply say c is the root of 61. And if we want to approximate this, we can type in the square root of 61 and get that as an approximation. So it turns out this action we call solving a triangle, meaning filling in all the side lengths and angles that we weren't given, can be done with either one acute angle and one side, assuming it's a right triangle, or with two sides, assuming it's a right triangle. That's all we need. Let's do an application problem, shall we? So we have a certain character is standing 123 feet from the base of a flagpole and looks up to the top of the flagpole. So let's start with a picture. Here is my flagpole, and the base is 123 feet away from the character, and the angle of elevation is 26 degrees 40 minutes, meaning from the location of the character's eyes, if we draw up to the top of the flagpole right there, this angle is 26 degrees and 40 minutes. If her eyes are 5.2 feet above the ground, so this height is 5.25 feet, find the height of the flagpole, so this entire height right here. So what we need to understand is there is a right triangle right in here, and we have that the base of this right triangle is 123 feet. So perhaps we will label this side A, and once we find this, we can add 5.25 to get the total height of the flagpole. Well, that looks like opposite over adjacent, so we shall use tangent. Tangent of 26 degrees 40 minutes is going to equal opposite over adjacent, which means A is simply multiply 123 over times tangent of 26 degrees and 40 minutes. Now, we can perform a conversion right here and say this is the same thing as writing 26 full degrees plus 40 minutes times 1 degree for every 60 minutes. And once we have this, we will have that as the full angle measure in degrees, and then we can do 123 times tangent of. If I hit enter now, what will I get? Always check your mode. I am in radians, which means if I enter this now, the calculator will understand this is 26.6 repeating radians. I don't want that, so I have two options. I can either put the degree symbol and get the right answer, or I can change my mode to degrees and get the right answer. Either one works. I'm going to stay in radians and hit the degree button just for good measure. So that is A equals 61.77. The units are in feet because our other side length was in feet, which means the height of the flagpole is A plus 5.25 feet, which is going to give me this plus 5.25. Hit the button, is 67.02 feet. And I sort of arbitrarily rounded to 2 decimal places because I felt like it, mainly because they gave me 2 decimal places there. Shall we do one more? So here, at a certain time, the length of the shadow of a building, 34.09 meters tall. Okay, so if I were to draw a building, perhaps like this, I could say this building height is 34.09 meters. Then there is a shadow that's 37.62 meters long. This is 37.62 meters. Always draw a picture. Now, I want to know the angle of elevation at the sun. Oh, so the way shadows work is if the sun is up here, the light's going to sort of clip the corner of the building and produce this triangle. So if the sun is up here, very small sun, then the angle right here is the angle of elevation to the sun. Well, we have a right triangle with sides 34.09 and 37.62. So in fact, we could use tangent of the angle is opposite over adjacent, 34.09 divided by 37.62. And we would like the angle. So we're going to say, let's do tangent inverse of that number, because this value is going to be the output of the tangent function. So to do tangent inverse, we would switch the input and the output, and our answer would become the angle theta. Let's hit these buttons. Trig, tangent inverse of 34.09 divided by 37.62, and hit the button. Am I in radians or degrees? Oh, I'm in radians. So my answer, theta, that the calculator gave me is 0.736 radians. Is this what I wanted? Maybe, maybe not. Usually when we're dealing with right triangles, we prefer degrees. It's just a preference we have from a long time ago. I'm going to go ahead and change the mode to degrees and copy that over. I will have 42.18 degrees. Once again, arbitrarily rounded to 2 decimal places because I felt like it. And so this is how it works. Right triangles, super useful. Well, thanks for tuning in. I'll see you again next time.